Hello, it's Keith here, and this is lesson 6 of the platform-specific series of my PDP11 programming tutorials, and we're looking at the UKNC again. We're going to be reading in from the keyboard this time directly, not by using the console emulation. Now, the UKNC and its keyboard are a little bit interesting because, like a few other systems, the UKNC has two processors, a main processor and a sub-processor, also known as the peripheral processor on the UKNC, and the keyboard can only be accessed from the sub CPU. So what we're going to have to do is we're going to have to pass a program to the sub CPU and read in from the keyboard on the sub CPU. Now, how does the keyboard work? Well, it's a little bit interesting. Basically, we have a port that we can read in only from the sub CPU, a memory map port. If we read in from the port 17702 in octal from the sub CPU only, not from the main CPU, we will get the data from the keyboard. Now the keyboard has its own, I guess it's got its own chip that's sending data, updating the status, and we just read in a single byte from that, and that will tell us the commands that are being passed from the keyboard itself. Now what we're going to do in this example is we're going to write an interrupt handler that is going to read in that input. So basically the keyboard will cause an interrupt, and that interrupt handler will then process the interrupt read in from the keyboard and do whatever we want with it. And what we're going to do today is we're going to read in two things. Firstly, we're going to read in the raw data. So you can see here on the leftmost byte is the raw data, and if I press down space you'll see it says 4B. When I release space you'll see it says 8B, and 4B is the code for space key down, and 8B is the code for space key up, although there's a little bit of an issue there. Now what I'm also doing is I'm then converting the various key presses into a simulated joystick. I refer to it as a joystick on all systems just for code compatibility, but it's of course the keyboard. So I'm doing 1 bit per direction, so we've got up, down, left, right, and then some fires here, and so each bit of that second byte is representative of a direction: up, down, left, right, fire 1, 2 and 3, and then I've got escape for a pause key for the 8th bit there. So that's what we're doing. We're reading in raw data and we're also converting that data. Now this interrupt handler is running from on the sub CPU, and all we need to do is write some program code to do the job that we want, in this case reading in the data and converting it to directions, and then we write the address of our interrupt handler to the memory address 300, which is the system address for the interrupt handler for the keyboard. So we are effectively overwriting the system one when we do that, but I never use system stuff if I can avoid it, so that's not going to matter. And that's what we're doing today. Now if we just move this out of the way, there is a rather tricky thing, because when we read in from port 17702, the key down values and the key up values are different. Now the bit 7, which is the sign bit if we read in a single byte, which is handy, the bit 7 will be a 0 if a key has been pressed down, and then we will get 7 bits which are the key code. Now these key codes you can see here, there's a little table here, or if you go to the UKNC page of my website you can see there's a nice big table here. I'm showing hexadecimal, but of course you would often want to use octal, and the space key that we just looked at is 4B in hexadecimal, or 113 or 75 in octal or decimal. That's the key that we were just testing there. Now when the key down is pressed, the top bit will be 0 and the other 7 bits will be the key code. However, when the key up is released, when the key is released rather, the top bit will be 1, then the next 3 bits will be unused and we will only get 4 bits of the key code. So effectively we only get 1 nibble of the key code, and that's why when we press space down we get 4B, which is the key code for space. When we release it, the top bit is 1, so we get an 8 in the first nibble, so we get an 8, but then we get the B, which is the bottom nibble of the 4B part. Now this means that while we can uniquely identify the key that was pressed down when a key down event occurs, we cannot uniquely identify the key that was released when the key up occurs, at least to my knowledge. Now if there's some clever thing that I'm missing, then please let me know. I had to use Google Docs and Google Translate and translate Russian documentation to get this. So this is the best I understand of it, that there is no way of uniquely identifying the key, and that what we've got here is the best that is feasible, I think. Now, what we're not going to discuss today, though, is how to transfer programs to the sub CPU. The code is included in today's example. I covered it before in one of my previous episodes, so please take a look at that. We're going to be discussing just the new code and how we're running things today. So we are using this show hex routine here to show the values to the screen, and what we're doing here is we're reading in 2 bytes from this test keyword, the 16-bit value here, the first one here which is the raw data, and the second one here which is my simulated joystick, and we're using show hex to show them to the screen in an infinite loop. All of the work is being done by the sub CPU in this key command here, which we've transferred and executed, and that has installed our interrupt handler, which is setting the test key bytes here, and you can see we've got the initial value of them there. We're setting all the bits to 1 there. Okay, so let's take a look at this test key routine, which is where all the cleverness is happening. Okay, so here it is. Now this will be run at the sub CPU, and we don't know the address it's going to run at, so we're calculating relative addresses in some cases here. So this key handle routine is the interrupt handler we want to install. So first we're calculating the relative address based on the program counter, and that is going to calculate the address that this has ended up running on the sub CPU. What we're then doing is we're moving that address to the address 300 in octal on the sub CPU, which is the address of the interrupt handler. So we've now effectively installed the interrupt handler, and that is now going to get any key presses when they occur. All we're doing here is we're setting the flag end, which is part of the code that is that has transferred this program to the sub CPU and executed it. That is telling the main CPU the sub CPU has finished executing that code and it can carry on. Okay, so here's our key handler. First, what we're doing is we're backing up all of our registers here. We're backing up R0, R1 and R2, which are the only 3 I'm using, backing up into the stack. We're also backing up 177010, which is the wrap address. Now, the wrap device, if you don't know, is the device that allows us to write to any address in memory, and this is how the sub CPU can access the main CPU memory. We used it again up here. We write the address we want to change to 177010, and then we write the 2 bytes of data that we want to transfer to 177014 and 177015. Now we're wanting to write to the test key address. Now this contains a 16-bit value up here, but basically the banks of memory that make up the main CPU's memory are multiplexed. There's basically 2 banks that make up alternating bytes of that memory, and so to calculate the correct address we're dividing by 2, and then we write the first byte to 177014 and the second byte to 177015 here. So that's how we use the wrap device, but because the wrap device is going to be being used by other things other than our interrupt handler, we're backing up the address that it's pointing to at the start of our interrupt handler, and we're restoring it at the end. And at the end of our interrupt handler, we're returning with an RTI. So that's what we need to do to have a valid interrupt handler. Okay. Now, there's a couple of things we're doing here. The first thing we're doing is we are reading in the raw value from the keyboard, and that is using port 17702. That's the raw data from the keyboard processor. So this is going to be the byte in the format discussed before that's going to tell us whether the key is down or up. Now, the first thing we're doing for testing and also possibly for more simple stuff is we're storing that raw data to the first byte in our 16-bit return at test key. So we're storing that directly as is, and then what we're going to do next is going to depend on whether we've got a key down routine or a key up routine, and that's defined by the top bit. So if the top bit is 1, then the branch if minus would occur, because the top bit is usually the assign bit. So if that's a 1, a key has been released and we're going to run the key up routine. Otherwise we're going to run the key down routine, and in both cases these are using a key map for the simulated joystick, and here is the key map. Now the key map's in a very simple format. We have a byte which defines the key code in octal, and then we have a byte that defines the mask for the bit that key will change. So this first key is the up key, literally the up key, and that is going to use bit 0, which has a value of 1. The down key is going to have a value of 2, that's bit 1. Then 3, bit 3, that's 4, then bit 4, which is 10 in octal, then and so on. So these are the keys we're using, and we're using up, down, left, right, space, enter, shift and escape, I believe these are, and these are the correct key codes for those. So of course if you wanted to use different keys and You probably want to use better fire keys than the ones I've selected. I think there's some nasty key clash with these because of that problem where when a key is released, we don't get all the bits that tell us which that key was. So you need to select keys that don't have matching bottom nibbles. The bottom 4 bits should really be unique for all of them. If you can, I think that's going to give a better result. Anyway, so we've got our key map, but how we're going to use it is going to depend if our key is down or our key is up. So we're branching to a different routine if our key is up. If our key is down, what we're going to do next is we're going to move bytes in from the key map. This is the bytes that represent the key code, and we're going to move those into R2. When we get a 0, then we've reached the end of the list. You see, the list, there is no such key code as 0. So when we get a 0, we're at the end of our list. So that's why we are repeating until we've got a 0 there. If we've not got a 0, we're comparing that R2 value to the R0 value, which is the value we read in from the hardware. So we're seeing if the key code matches, and if it does, we're immediately going to key found. This is the only one key code can possibly match. So if we found it, we're giving up. If we've not found it, we're skipping over the bit mask, which represents what we would want to do if the key was a match. And then we're repeating, reading in the next key code, and so on. Now, once we find the correct key code, what we're doing is we're clearing the bit in port 177015, which is the second byte of the wrap device. And this is how I've got this set up so that when we press a key, that bit goes to 0 here. So when I press up, bit 0 goes to 0. When I press down, bit 1 goes to 0 here. And so we are clearing the bits so that those keys are setting the bit to 0 for the respective key. So we're using a bit clear here of the mask for the key that was detected with the second byte in the wrap device, which is the second byte shown to the screen here. So that's what we're doing there. Now, once we've found that, we're then just returning here and setting all of our registers back to the correct values and resetting the wrap device so that any other memory access will occur normally. Now, if we have got a key up event, remember the top bit will be 1 by default. So first what we're doing here is we're clearing that bit in the test value here. So we're clearing that there. Then what we're doing here is we're moving a byte again from our key map here. So we're moving one of these bytes in, which will be the key press. But there's a problem because when our key is released, we're only getting 4 bits of the key code. So what we're doing here is we're clearing the top nibble of the key code before we do the comparison. Now, when a comparison doesn't match, we're basically doing the same as before, skipping over the mask and then carrying on. But when it does match, we want to set the bit so that the bit goes back to 1 when the key is released. But there might be multiple this time that match because remember we've only got 4 bits of the released key, so we may not have an exact match. So because of that, we're setting the bit for this match, but then we're continuing with any other possible matches until we get to the end of the list, no matter what. So there we go. So that's what I've done here to allow for this code to work. And as I say, it works reasonably well. Up, down, left, right, space. There is some issues with regards to multiple key presses at the same time. I think left and space is playing up. So I don't think that space is probably the best key to use for fire buttons, but it was just a simple test. And what we're going to do next time is we're going to look at combining this with a sprite routine, and we're going to move a smiley around the screen. This is a beginner's test I like to do, which is where we move a simple graphic around the screen. It's good for a getting started example if you're looking to play with this. Now, if you've liked what you've seen here, you can back me on Patreon. That's the best way for you to support me keep making this content, because weird systems like the UKNC, this is something that I purely do because I have people who back me who are interested in the PDP11 and the UKNC. So if this is the kind of thing you want to see, please consider backing me. This is the only way I can justify spending my time on strange stuff that I've never owned and didn't really have a natural interest in. Anyway, hope you've enjoyed this today. Thanks for watching and goodbye.